September 1943. A B-17 Flying Fortress limps back to England, riddled with bullet holes. The navigator is dead. The ball turret gunner is wounded. But the worst part isn't the damage they took over Germany. The worst part is that their fighter escort turned back over Holland, leaving them defenseless for the deepest part of their mission. The Luftwaffe knew exactly where American protection ended, and they waited like sharks beyond that invisible line in the sky. By October 1943, the U.S. 8th Air Force had lost so many bombers on deep penetration raids that they had to suspend daylight bombing missions into Germany's heartland. The strategic bombing campaign was failing, not because American bombers weren't tough enough, but because no Allied fighter could escort them all the way to Berlin and back. The Germans owned the high-altitude airspace over their territory, and they knew it. But by March 1944, everything changed. American fighters were suddenly appearing over Berlin, engaging Luftwaffe interceptors at altitudes where they'd once been untouchable, then escorting bombers all the way home. German pilots were stunned. How did the Americans suddenly develop a fighter that could do what had been aerodynamically impossible just months before? The answer wasn't tactics, it wasn't courage, it was metallurgy, and it all came down to one man's breakthrough with an alloy that shouldn't have existed. Developed under such secrecy that even the engineers building the engines didn't fully understand what they were working with. This is the story of how the P-51 Mustang went from a mediocre low-altitude fighter to the war-winning weapon that broke the Luftwaffe's back. But more importantly, it's the story of the forbidden science that made it possible. To understand what made the P-51 Mustang's transformation so revolutionary, you first need to understand the physics problem that was killing Allied airmen by the thousands. In 1943, there was a hard ceiling in aerial warfare, and it wasn't theoretical. It was brutally real. Most American fighters could reach 25,000 feet, maybe 28,000 feet if you pushed them. But at 30,000 feet and above, they were gasping. The thin air starved their engines. Performance degraded. Climb rates plummeted. And that's exactly where the Luftwaffe positioned their interceptors, looking down at the American bomber formations like predators on high ground. The Bf-109G and the FW-190 could fight effectively at 35,000 feet. They could dive down through bomber formations, rake them with cannon fire, then climb back up to safety before American escorts could react. The altitude advantage meant German fighters controlled when and where they engaged. They could pick their fights, and American fighter pilots couldn't follow them up. Now, every piston engine faces the same problem at altitude: air density. At sea level, every liter of air contains a certain amount of oxygen. Your engine's cylinders suck in that air, compress it, mix it with fuel, and ignite it. The combustion drives the pistons. More air equals more power. But as you climb, air gets thinner. At 18,000 feet, the air pressure is half what it is at sea level. Half the air means half the oxygen. Half the oxygen means half the power. Your 200 horsepower engine suddenly becomes a 600 horsepower engine. You can push the throttle all you want, but the atmosphere doesn't care. The solution to thin air is supercharging. A supercharger is essentially an air compressor bolted to your engine. It spins at tremendous speed, cramming more air into the cylinders than the atmosphere would normally provide. With a supercharger, you can restore sea-level air pressure to your engine even at 25,000 feet. Problem solved, right? Not quite, because superchargers create three murderous problems of their own. First, compressing air generates heat, a lot of heat. When you squeeze air molecules together, they get hot. That superheated air is less dense than cool air, which defeats the whole purpose. You need to cool it back down before it enters the cylinders, which requires an intercooler. That's extra weight, extra complexity, extra points of failure. Second, spinning a supercharger takes power. You're literally stealing horsepower from your engine to compress its own air. A single-stage supercharger might consume 150 horsepower just to spin the compressor. That's 150 horses that aren't pushing your airplane forward. Third, and this is the killer, single-stage superchargers hit a performance wall. They work brilliantly up to a certain altitude, usually around 20,000 feet. But push higher, and they can't compress enough air to maintain power. The engine starts dying again. You need more compression, but if you spin the supercharger faster, it generates so much heat that you're back to problem number 1, and the heat becomes unmanageable. The British figured out the theoretical solution in 1940. Two-stage supercharging. Take the air, compress it once, cool it down, then compress it again, cool it again, and only then feed it to the engine. This could theoretically maintain power up to 40,000 feet. But theory is easy. Engineering reality is hard, because now you're asking one component to withstand conditions that no piston engine had ever faced before. The second-stage supercharger sits right behind the engine, bathed in exhaust heat. It's spinning at up to 30,000 RPM. The metal is subjected to centrifugal forces that want to rip it apart. The compressed air coming off the impeller is hot enough to glow. And you're asking this component to do this for hours on end. In combat, where your pilot is slamming the throttle open and closed, cycling between maximum boost and cruise power, creating thermal shocks that make metallurgists wake up sweating. The impeller blades are the critical point. They're thin to be lightweight. They're curved to direct airflow efficiently. And they're spinning so fast that the tips are experiencing forces equivalent to hundreds of times Earth's gravity. At high temperatures, for extended periods, normal steel fails. It softens at high temperatures, and the centrifugal force stretches the blades until they contact the housing, and the whole assembly destroys itself. You get maybe 20 hours of operation before catastrophic failure, if you're lucky. Normal nickel alloys do better, but not well enough. They can handle higher temperatures, but they still creep. That's the technical term for metal slowly deforming under sustained stress. Creep is insidious. The blades gradually stretch, millimeter by millimeter, until tolerances are exceeded and efficiency plummets. Your two-stage supercharger becomes a one-stage supercharger, then becomes a very expensive paperweight. This was the wall the British hit in 1940. They knew two-stage supercharging was the answer. They could build prototypes, but they couldn't make them reliable. Every test engine destroyed itself after 30 or 40 hours. You can't win a war when your fighters need engine rebuilds after every 10th combat mission. The problem wasn't engineering. It was materials science. They needed a metal that could withstand sustained operation at 750 degrees Celsius while spinning at insane speeds and resisting deformation. And in 1940, that metal didn't exist. At least, not officially. Let me take you to Hereford, England, 1940. The Wigan Works, officially known as Henry Wigan and Company, tucked away in the countryside of Western England. To a casual observer, it's a nickel alloy manufacturer, producing specialty metals for industrial applications. But inside its research laboratories, something extraordinary is happening, and it's wrapped in more secrecy than most military operations. The man at the center of this is Leonard Bessemer Pfeil. Yes, that Bessemer, he's the grandson of Sir Henry Bessemer, the man who revolutionized steel production in the 1850s. Metallurgy is literally in Leonard's blood. But where his grandfather worked with steel, Leonard is obsessed with nickel, and specifically, with pushing nickel alloys far beyond what anyone thought possible. Pfeil and his team are working on a problem that's borderline crazy. They want to create an alloy that remains strong at temperatures where most metals would be soft as butter. Conventional metallurgy says this is impossible. Metal strength comes from its crystalline structure. Heat disrupts that structure. Once you pass a certain temperature threshold for any given alloy, strength drops off a cliff. It's basic physics. You can't cheat thermodynamics, but Pfeil thinks you can outsmart thermodynamics. His approach is radical. Instead of trying to preserve the crystalline structure at high temperatures, what if you could create microscopic particles inside the metal that physically block the movement of dislocations in the crystal lattice. What if you could engineer obstacles at the atomic level that prevent creep even when the surrounding metal is hot enough to glow? This is called precipitation hardening, and it's not entirely new. But File is pushing it to extremes nobody has attempted before. He's working with a nickel-chromium base. Nickel for its high melting point and oxidation resistance, chromium for corrosion resistance. But then he's adding titanium and aluminum in carefully calculated proportions. When the alloy is heat-treated properly, the titanium and aluminum form gamma prime, precipitates, tiny particles of a nickel-titanium compound that are harder than the surrounding metal and distributed throughout the structure like reinforcing bars in concrete. The percentages matter enormously. Too little titanium, and you don't get enough precipitates. Too much, and they clump together and actually weaken the structure. The heat treatment is even more critical. The alloy has to be heated to above 1,000 degrees Celsius to dissolve everything into a uniform solution, then cooled at a precise rate to allow the precipitates to form with the right size and distribution. Get the cooling rate wrong, and you've just made expensive garbage. Field's team runs hundreds of experiments through 1940 and into 1941. They're casting test samples, heat-treating them, machining them into test pieces, then loading them into creep testing equipment, devices that hold the metal under constant stress at high temperature for hundreds of hours while measuring how much it deforms. This is grinding, tedious work. Most samples fail. The few that show promise lead to variations, and those variations lead to more failures, and gradually, painfully, they zero in on a composition that works. By mid-1941, they've got it. Mnemonic 80. The alloy contains roughly 75% nickel, 20% chromium, 2.5% titanium, 1.4% aluminum, and trace amounts of carbon and other elements. It can maintain useful strength at 750 degrees Celsius. It resists creep under high stress. It doesn't oxidize rapidly in hot air. And crucially, it can be machined and cast into complex shapes like turbine blades and supercharger impellers. But here's where things get weird. This alloy shouldn't exist, according to British export regulations and strategic materials policies. The UK in 1941 is under siege. Resources are carefully controlled. New alloys, especially ones with military applications, are supposed to go through official approval processes. They're supposed to be evaluated by government metallurgists, tested by the Ministry of Supply, and carefully allocated to the highest priority applications. There's a bureaucracy, a chain of command, a process. Mnemonic 80 bypasses all of that. The reason is Frank Whittle. He's simultaneously a genius and a headache for the British establishment. He invented the practical jet engine in 1937, but the Air Ministry initially dismissed his ideas. Now, in 1941, they realize jets are the future. But Whittle's development program is chaotic. He's working with Rover to manufacture his engines, and it's going badly. The engines are destroying themselves. The turbine blades can't handle the heat and stress. Whittle needs better materials yesterday, but the official channels are slow and bureaucratic. Somebody connects Whittle to Feel. The meeting is almost certainly unofficial. File shows Whittle the test data for Mnemonic 80. Whittle immediately grasps what he's looking at. This is the material that can make jet engines practical. Within weeks, File is casting turbine blades in Mnemonic 80 for Whittle's Power Jet's W2 engine. They work. The engine runs longer and at higher temperatures than any previous version. But here's the thing. This is happening in parallel to the official development programs. The Ministry of Supply doesn't fully know. The regulatory bodies don't fully know. Mnemonic 80 is being manufactured and used in cutting-edge jet engines before it's officially approved as a strategic material. It's not illegal exactly, but it's deeply irregular. And it's being kept quiet because if the bureaucracy knew, they might shut it down while they conduct proper evaluations and committee meetings. And there's a war on. and Whittle needs those turbine blades now. Now, you might be thinking, this is interesting, but what does this have to do with the P-51 Mustang? The Mustang doesn't have a jet engine. It has a piston engine. Why does it need exotic turbine blade alloys? The answer is that two-stage supercharging creates conditions inside a piston engine that are remarkably similar to what's inside a jet turbine. The second-stage impeller is essentially a small turbine blade, experiencing similar temperatures, similar stresses, similar centrifugal loads. And in 1941, when Rolls-Royce is trying to develop a two-stage supercharged version of their Merlin engine, they're hitting the exact same materials problem that Whittle hit with his jet engines. This is where the threads start to come together. But to understand how, we need to talk about another brilliant engineer who's about to enter the picture. Stanley Hooker doesn't look like a war hero. He's a mathematician, thin, bookish, with thick glasses and a quiet demeanor. In 1938, when he joins Rolls-Royce, he's given an unusual assignment: figure out why the Merlin engine's supercharger is so inefficient. Hooker approaches this like the mathematician he is. He doesn't just tinker with the hardware. He derives the fundamental equations that govern how air flows through a centrifugal compressor. He maps the velocity profiles. He calculates the losses due to turbulence, friction, and inefficient blade geometry. And he realizes the Merlin's supercharger is wasting enormous amounts of energy. The existing design was developed by trial and error. It works, sort of, but the impeller blades aren't optimally shaped. Air is hitting them at the wrong angles, creating turbulence. Energy that should be going into compression is being dissipated as heat and noise. Hooker calculates that the efficiency is only about 68%. For every 100 horsepower spent spinning the supercharger, only 68 horsepower worth of useful compression is happening. The other 32 horsepower is just being wasted. Hooker redesigns the impeller blades using aerodynamic principles. He changes the blade angles, the curvature, the inlet geometry. He adds guide vanes to straighten the airflow. When the new design is tested in 1940, efficiency jumps to 76%. That might not sound like much. It's only an 8-point improvement. But the impact on engine power is dramatic. The Merlin 45 with Hooker's improved supercharger produces 30% more power than earlier versions at high altitude. 30%. That's the difference between the Spitfire being competitive with the Bf-109 and being dominant over it. The Merlin 45 goes into production in October 1940, powering the Spitfire MKV, which becomes the most produced Spitfire variant. Hooker has just changed the course of the air war over Britain, but he's not done. In late 1940, the Air Ministry asks Rolls-Royce for a Merlin that can maintain power at 40,000 feet. They suggest turbocharging, using the engine's exhaust gases to drive a turbine that spins the compressor. Turbocharging is what the Americans are using on their B-17 and B-24 bombers. It works, kind of, but it's complex and unreliable. Hooker declines their suggestion. Instead, he proposes two-stage supercharging. Take the air, compress it with a first-stage supercharger, cool it with an intercooler, then compress it again with a second-stage supercharger, cool it again with another intercooler, then feed it to the engine. This will maintain sea-level air pressure all the way up to 40,000 feet. The Air Ministry is skeptical. Two-stage supercharging has been tried before, and it's always failed due to reliability problems. The second-stage impeller can't survive the heat and stress. Hooker acknowledges this is the key challenge, but he's confident he can solve it with better design and materials. What Hooker has, that previous attempts didn't, is access to mnemonic alloys. Remember, by late 1941, mnemonic 80 is being used in Whittle's jet engines. The knowledge that this alloy exists and works is spreading through Britain's small community of advanced engine designers. Hooker connects with Field's team at Wigan Works. He explains the supercharger problem. File tells him about mnemonic 80. The two-stage Merlin development becomes a parallel track. The Air Ministry has officially commissioned it, But they don't fully understand the materials challenges or how Rolls-Royce plans to solve them. Hooker's team is working with mnemonic 80 impellers before the alloy is officially approved for aircraft engine use. They're machining prototypes, testing them to destruction, iterating the design. The results are extraordinary. The mnemonic 80 impellers can withstand the heat and stress of the second stage. They don't creep. They don't fail after 30 hours. They run for hundreds of hours at full power. The two-stage supercharger works. By early 1942, Rolls-Royce has a functioning prototype, the Merlin 61. It produces 1,565 horsepower at 12,150 feet altitude. But more importantly, it maintains over 1,390 horsepower at 23,500 feet. For comparison, the single-stage Merlin 45 produces only about 1,000 horsepower at that altitude. The performance improvement is staggering. The Merlin 61 is first installed in the Spitfire Mk9, which enters service in July 1942. The timing is critical. The Focke-Wulf FW-190 has just appeared over France, and it's outperforming all existing British fighters. The FW-190 can climb faster and fight better at altitude than the Spitfire Mkv. British pilots are getting killed. The Spitfire Mach 9 with its Merlin 61 restores the balance. Suddenly, British fighters can climb with the FW-190 and fight effectively above 30,000 feet. But Hooker and his team aren't thinking about the Spitfire. They're thinking about range. Because the two-stage Merlin doesn't just produce more power at altitude, it's more fuel efficient. The improved supercharger efficiency means less wasted energy. An engine that wastes less energy burns less fuel. An engine that burns less fuel can fly farther on the same amount of gasoline. This is the breakthrough that nobody fully appreciated in 1942. The two-stage Merlin, with its mnemonic 80 supercharger components, doesn't just enable high-altitude performance. It enables long-range high-altitude performance. And that combination is about to meet an airframe that was specifically designed for efficiency and range. Enter the North American P-51. P-51 Mustang. The P-51 Mustang's origin story is one of the great ironies of World War II. It was designed to a British specification, initially rejected by the U.S. Army Air Forces, and only became legendary after it was re-engined with a British power plant. The Americans nearly missed out on their own war-winning fighter. In 1940, the British Purchasing Commission approached North American Aviation with a request. We need fighters, lots of them, and we need them fast. Can you build us some P-40s under license? North Americans' response was audacious. We can design you a better fighter in the same time it would take us to set up P-40 production. The British were skeptical, but intrigued. North American had never built a fighter before. But they had something many established fighter companies lacked: a brilliant chief designer named Edgar Schmude, and a culture of engineering innovation. Schmude had worked on the Messerschmitt Bf 109 before emigrating to America. He understood what made a fighter efficient. The Mustang design was fundamentally different from other American fighters. The P-47 Thunderbolt was big and powerful, built like a tank. The P-38 Lightning was twin-engined and fast, but complex. The Mustang was sleek. Schmude obsessed over drag reduction. The Mustang has a laminar flow wing, thinner and more aerodynamically efficient than conventional wings. The fuselage is carefully contoured to minimize turbulence. The radiator intake is positioned under the fuselage in a way that actually produces a small amount of thrust through what's called the Meredith effect. The hot air from the radiator exits faster than it enters, creating a net forward push. The result is an airframe that's slippery. It cuts through the air with less resistance than any other fighter of its era. In wind tunnel tests, the P-51's drag coefficient is nearly 30% lower than the P-47's. That means for the same engine power, the Mustang will fly faster. Or, more importantly, for the same speed, the Mustang will burn less fuel. The British received their first Mustangs in late 1941. They're powered by the Allison V17 10 engine, which is good at low altitude but struggles above 15,000 feet because it only has a single-stage supercharger. The RAF uses these early Mustangs for low-altitude reconnaissance and ground attack. They're fast at low level, but they're not the high-altitude escort fighter the Allies desperately need. Meanwhile, the U.S. Army Air Forces are conducting their disastrous daylight bombing campaign over Germany. The doctrine sounds good on paper. Heavily armed B-17 and B-24 bombers in tight formations can defend themselves with massed machine gun fire. They don't need fighter escort deep into Germany, except the doctrine is wrong. German fighters tear them apart. The worst period is October 1943, when 4 major raids in 1 week result in the loss of 148 bombers and nearly 1,500 aircrew. The raids on ball-bearing factories at Schweinfurt and Regensburg are particularly devastating. 60 bombers lost in a single mission. The strategic bombing campaign is on the verge of collapse. The 8th Air Force doesn't have a fighter that can escort bombers to Berlin. The P-47 Thunderbolt is tough and powerful, but its range is limited. Even with external drop tanks, it can only reach western Germany. The P-38 Lightning has the range, but it's unreliable, and its engines struggle in the cold air at altitude. German pilots have figured out that if they stay out of range until the American escorts have to turn back, they can attack the bombers with impunity for the last 300 miles into the target and the first 300 miles back. American bomber crews are dying because of an altitude range problem. The fighters that can reach high altitude can't fly far enough. The fighters that have enough range can't fight effectively at altitude. The Germans own the airspace above 25,000 feet over their territory, and the bomber formations have to cross that airspace to hit strategic targets. And then, in late 1942, somebody in Britain has an idea. What if you took the Mustang's efficient airframe and paired it with the Merlin 61's 2-stage supercharger? The Mustang is already efficient at low altitude with the Allison engine. What if you gave it an engine that was efficient at high altitude? The idea is almost too simple. Fighter development usually involves designing a new airframe and a new engine simultaneously, with all the complexity that implies. This is just swapping engines in an existing airframe. But the engineering challenges are significant. The Merlin 61 is heavier than the Allison V1710. The center of gravity will shift. The engine mounts need to be redesigned. The cooling system has to be reconfigured. The propeller specifications change. Rolls-Royce undertakes the conversion as an experimental project, designated the Mustang X. They remove the Allison engine from a Mustang MKI and install a Merlin 61. The first flight is in October 1942, and the performance is remarkable. With the Merlin 61, the Mustang is fast at all altitudes. Top speed at 25,000 feet is 422 miles per hour, faster than any other Allied fighter. Climb rate is excellent. Service ceiling is above 41,000 feet. But the real breakthrough is range. The efficient airframe combined with the efficient 2-stage Merlin means the Mustang can fly farther on internal fuel than any other single-engine fighter. And with external drop tanks, the range becomes extraordinary. Over 1,000 miles with 2 75-gallon drop tanks. Enough to fly from England to Berlin and back with fuel to spare for combat. The U.S. Army Air Forces, which had previously shown limited interest in the Mustang, suddenly pay attention. In 1943, they order the Mustang into mass production with the Packard-built version of the Merlin 61, designated the V1650-3. The American version is designated the P-51B, and in early 1944, P-51 Mustang groups start arriving in England. The transformation of the air war is rapid and brutal. In March 1944, Mustangs escort bombers all the way to Berlin for the first time. German fighter pilots, who have spent months strategically positioning themselves beyond the range of Allied escorts, suddenly find American fighters waiting for them everywhere. At altitude, over Berlin, during what were supposed to be safe intercepts, the Mustang can match or exceed the performance of the Bf-109G and FW-190A at altitudes above 25,000 feet, and it can do it 600 miles from base. German pilots can't escape by climbing. They can't wait out the escorts. If they want to attack the bombers, they have to fight through the Mustangs. And increasingly, they're losing. By the end of May 1944, the Luftwaffe has effectively lost air superiority over Germany. Not because they lack pilots or aircraft, though attrition is terrible, but because they can no longer control when and where they engage. The Mustangs hunt them everywhere. The high-altitude sanctuary is gone. The D-Day invasion in June 1944 proceeds under nearly complete Allied air supremacy. German fighters barely appear over the beaches. By the end of 1944, P-51 Mustangs have destroyed over 4,000 German aircraft in the air. The strategic bombing campaign, which was failing in late 1943, succeeds in 1944. German industrial production is hammered. Oil refineries are destroyed. Transportation networks are shattered. The P-51 Mustang is the weapon that broke the Luftwaffe. But the Mustang doesn't work without the two-stage Merlin. The two-stage Merlin doesn't work without Stanley Hooker's aerodynamic improvements. And Hooker's design doesn't work without mnemonic 80 supercharger components that can survive the heat and stress. It all comes back to Leonard Bessemer Field and his team at the Wigan Works, creating an alloy that shouldn't exist in a development program that bypassed official channels, to solve a problem that was killing Allied airmen by the thousands. Let's talk numbers, because the transformation is quantifiable and stunning. In October 1943, before the Mustang arrived in numbers, the 8th Air Force flew 4 major bombing missions deep into Germany. They lost 148 bombers out of roughly 1,400 sorties, a loss rate of 10.6%. At that attrition rate, bomber crews had almost no chance of surviving their required 25-mission tour. The math was grimly simple. If you had a 10% chance of being shot down on each mission, your odds of surviving 25 missions were less than 8%. Most crews would be dead or prisoners before they completed their tour. By spring 1944, with Mustangs escorting the bombers, the loss rate dropped to under 2%. The exact figure fluctuates by mission, but 2% is representative. That changes the survival equation dramatically. With a 2% loss rate per mission, a crew has a 60% chance of completing a 25-mission tour. Still dangerous, but survivable. The difference between an 8% survival rate and a 60% survival rate is the difference between a suicide mission and a viable military campaign. The Mustang's impact wasn't just quantitative, it was psychological. German fighter pilots had to fundamentally change their tactics. Before the Mustang, Luftwaffe doctrine was to avoid Allied fighters and focus on bombers. The altitude advantage and range limitations meant German pilots could usually disengage if they wanted to. After the Mustang, German pilots couldn't disengage. If they climbed away, the Mustangs followed them. If they dove away, the Mustangs followed them. If they tried to reposition for another attack run, the Mustangs pursued them. This forced German fighters to fight the escorts instead of attacking the bombers. Every minute a Bf-109 spent dogfighting a Mustang was a minute it wasn't firing cannon shells into a B-17. The bombers got through. And because the Mustangs could stay with the bombers all the way to the target and back, German pilots couldn't wait them out. The range issue was critical. The P-51B carried 184 gallons of internal fuel in 6 fuselage tanks. With 2 75-gallon drop tanks, total fuel capacity was 334 gallons. The two-stage Merlin burned about 70 gallons per hour at cruise power settings. That gave the Mustang nearly 5 hours of endurance, enough to fly from England to Berlin and back, a distance of about 150 miles, with 30 minutes of combat time at full power built in. By comparison, the P-47D Thunderbolt carried 305 gallons internally, and could carry two 150-gallon drop tanks for a total of 605 gallons. But its R2800 radial engine burned 100 to 120 gallons per hour at cruise. Range was only about 950 miles with drop tanks, and that didn't include combat reserves. The Thunderbolt could reach western Germany but not Berlin, and because its fuselage was draggy, it burned more fuel for the same distance covered. The P-38 Lightning had better range than the Thunderbolt, but it was plagued by engine problems in the cold European air. Its turbocharged Allison engines would lose power at altitude, and pilots reported frequent engine failures. Reliability in combat is worthless if the aircraft doesn't make it back to base. The Mustang was the only Allied fighter that combined high-altitude performance, long range, and reliability. And all three of those characteristics depended on the two-stage Merlin with its mnemonic 80 components. Here's the deeper metallurgical point that's often missed. Mnemonic 80 wasn't just strong at high temperatures. It was stable. Stability matters enormously in combat conditions. An engine in combat cycles through power settings rapidly. Full throttle for takeoff, cruise power for transit. Full throttle again for combat. Cruise power for the return flight. Each power change creates a thermal cycle. Heat up, cool down, heat up, cool down. Thermal cycling causes fatigue. Metal expands when hot, contracts when cool. Do that enough times, and microscopic cracks form. The cracks propagate. Eventually, the component fails catastrophically. Conventional alloys might survive 50 thermal cycles before cracks appeared. Mnemonic 80 could handle 500 cycles. That's an order of magnitude improvement. It meant Merlin engines could operate for 500 hours between major overhauls instead of 50 hours. It meant a fighter could fly 100 combat missions instead of 10 before needing an engine replacement. Reliability determines operational availability. If your fighters spend more time in maintenance than in the air, you effectively have fewer fighters. The Mustang's reliability, enabled by Mnemonic 80's stability, that more of the P-51s on the roster were actually available for missions. The 8th Air Force could launch larger formations with more escorts, which meant better protection for the bombers, which meant lower losses, which meant sustained operations. This is how one alloy changed the strategic calculus of the air war. Now, let's address the forbidden aspect. Mnemonic 80 wasn't literally forbidden, but its development and deployment existed in a gray zone that would have been scandalous if it had become public during the war. The British government in 1941 was operating under extraordinary secrecy constraints. The Official Secrets Act was rigidly enforced. New military technologies were compartmentalized. Information was shared on a strict need-to-know basis, and strategic materials were carefully controlled. Nickel, chromium, and titanium were all restricted materials. You couldn't just develop a new nickel-chromium-titanium alloy and start manufacturing it without government approval, except. That's essentially what happened with Mnemonic. 80 Files team at Wigan Works developed it as an internal research project. When Frank Whittle needed better turbine blade materials for his jet engine, Fields supplied them through informal channels. The alloy went into production and use before it went through official evaluation and approval. Why did this happen? Because Whittle's jet engine program was itself chaotic and outside normal channels. Whittle was a maverick genius who had been ignored by the Air Ministry for years. His engine was being developed by Rover, a car company with no aviation experience, and the relationship was dysfunctional. Whittle needed results, and he needed them faster than government bureaucracy could move. Field and Whittle connected because Britain's advanced engine community was small. Everyone knew everyone, and in wartime, results mattered more than procedure. If Mnemonic 80 worked, and if it made jet engines practical, nobody was going to stop it because the paperwork wasn't filed correctly. But this created a legal ambiguity. Technically, Mnemonic 80 should have been classified as a strategic material, and its use controlled by the Ministry of Supply. In practice, It was being manufactured and used in combat-critical applications without formal classification. If this had become public, it would have been embarrassing. If Germany had learned the composition and production methods for Mnemonic 80, it would have been disastrous. They could have improved their own engine capabilities. So the whole thing was kept very quiet. Mnemonic 80 was produced. It was used. It worked brilliantly. But very few people outside a small circle of metallurgists, engine designers, and security-cleared officials knew the details. This is why historical records on Mnemonic 80 are sparse. The alloy's role in winning the war was real, but it wasn't publicized. After the war, when secrecy restrictions eased, the story was overshadowed by more dramatic narratives like radar, code breaking, and the atomic bomb. But the metallurgy was just as important. You can have the best tactics and the best pilots, but if your engines fail, you lose. The forbidden alloy wasn't forbidden by law. It was forbidden by the silence of classified information and the obscurity of technical details that most historians don't find exciting. But the pilots who flew Mustangs to Berlin and came home alive owed their lives to that alloy, whether they knew it or not. Let's bring this full circle to the human level. Imagine you're a B-17 pilot in early 1944. You're 22 years old. You've flown 10 missions over Germany. And you've watched friends die. You've seen bombers explode in mid-air. You've felt the terror of Bf-109s diving through your formation. Cannon shells ripping apart the aircraft around you, and knowing your fighter escort has already turned back because they're out of range. Now it's March 1944. You're briefed for another Berlin mission. The room goes silent because everyone knows Berlin means maximum exposure to German fighters. But then, the intelligence officer says something you've never heard before. Escort fighters will accompany you all the way to target and back. You don't believe it. It's not possible. No single engine fighter has the range. But on takeoff, you see them. Silver P-51 Mustangs, dozens of them, forming up alongside your bomber formation. And they stay with you. Over Holland, over Germany, all the way to Berlin. You watch them engage Bf-109s at 30,000 feet, turning and burning with them, driving them away from the bombers. You watch them chase down FW-190s that try to reposition for attack runs. Your bomber takes flak damage over the target, but no fighter attacks. On the way home, a P-51 pilot spots your damaged aircraft, drops down, and escorts you specifically, warding off any German fighters that might try to pick you off as a straggler. You make it back to England. You land, you're alive, and you know that 10 weeks ago, you wouldn't have been. That pilot flying the Mustang might not know what Mnemonic 80 is. The B-17 crew certainly doesn't. But they're all alive because of a metallurgist's breakthrough and an engineer's redesigned, supercharger and an airframe designer's obsessive. Attention to aerodynamic efficiency. 3 different innovations brought together in one aircraft, solving a problem that was killing thousands of people. That's the real story of the P-51 Mustang. Not that it was a great fighter. Lots of aircraft were great fighters. But that it was the right combination of technologies at the right moment to solve a critical strategic problem. And one of those technologies was an alloy developed in secret, deployed without official approval, and kept quiet for decades after the war. Mnemonic 80 didn't stop with World War II. After the war, when jet engines became standard for military and commercial aviation, mnemonic alloys became the foundation of gas turbine technology. Mnemonic 90 was developed in 1945 with even better high-temperature properties. Mnemonic 105 came in 1960. These alloys enabled higher turbine inlet temperatures, which meant more efficient jet engines, which meant commercial aviation became economically viable. When you fly on a modern airliner, the turbine blades in those engines are descendants of Field's work. They're more advanced, single-crystal superalloys, thermal barrier coatings, directional solidification. But the fundamental principle is the same. Nickel-based alloys with precipitate hardening to resist creep at high temperatures. File's breakthrough in 1941 established the metallurgical path that aviation has followed ever since. Stanley Hooker went on to design the Pegasus, vectored thrust engine that powered the Harrier jump jet. He returned to Rolls-Royce in 1971 to save the WWII engine program after the company went bankrupt. He was knighted for his contributions. His autobiography is titled "Not Much of an Engineer," a sarcastic reference to Ernest Hives's comment when Hooker first interviewed at Rolls-Royce, and Hives saw his mathematical qualifications. Hooker proved that mathematicians can be extraordinary engineers when they understand the physics. Edgar Schmood, who designed the Mustang's airframe, went on to design the F-86 Sabre, which dominated the skies in the Korean War. The Sabre borrowed many aerodynamic principles from the Mustang. Schmood died in 1985, largely forgotten outside aviation circles, but his designs killed more enemy aircraft than any other American aircraft designer in history. Leonard Bessemer File never achieved public fame. He continued working on nickel alloys after the war and died in 1968. There are no monuments to him. His name appears in technical metallurgy papers but rarely in popular histories. Yet his work enabled the two most important aviation technologies of the 20th century: the jet engine and long-range high-altitude piston fighters. So, what's the lesson here? There are a few. First, wars are won by the boring stuff, not by tactics and bravery alone, but by logistics, materials, science, production engineering, and relentless attention to technical details. The Mustang's performance wasn't magic. It was thermodynamics and metallurgy. The pilots were brave, but the metallurgists and engineers gave them tools that worked. Second, innovation often happens outside official channels. Bureaucracies are necessary, but they're slow. In a crisis, results matter more than procedure. File's development of Mnemonic 80 bypassed formal processes because there wasn't time for formal processes. Hooker's redesign of the Merlin supercharger happened fast because Rolls-Royce empowered individual engineers to make decisions. Schmoed's Mustang design was approved because North American aviation promised results, not studies. Third, technologies converge in unexpected ways. The Mustang succeeded because three separate innovations, laminar flow aerodynamics, two-stage supercharging, and high-temperature alloys, came together in one aircraft. None of those innovations were developed specifically for the Mustang. They were independent breakthroughs that happened to be compatible. Finding those convergences is what systems engineering is about. Fourth, secrecy obscures history. We know about radar and ultra-code breaking and the atomic bomb because those stories were eventually declassified and publicized. But there were dozens of other breakthroughs in metallurgy, chemistry, production techniques, logistics that remained obscure because they weren't glamorous or because the details stayed classified. The forbidden alloy is a reminder that what's forgotten is sometimes as important as what's remembered. And finally, individuals matter. File, Hooker, and Schmood weren't inevitable. Their specific insights and talents shaped the technologies that shaped the war. Replace them with average engineers, and the Mustang probably doesn't become the weapon that broke the Luftwaffe. History has contingency. Small decisions and individual brilliance compound into world-changing consequences. By May 1945, when Germany surrendered, P-51 Mustangs had flown over 213,000 combat sorties in Europe. They destroyed 4,150 German aircraft in air-to-air combat and an additional 4,131 on the ground. The Mustang had the highest kill ratio of any American fighter, 19 enemy aircraft destroyed for every Mustang lost in combat. But the real victory wasn't the kill ratio. It was that the strategic bombing campaign succeeded. German industrial production collapsed. The oil refineries were destroyed, starving the Wehrmacht of fuel. Transportation networks were shattered, isolating German armies. By early 1945, Germany was functionally defeated. Not because their soldiers lacked courage or their generals lacked skill, but because their economy couldn't sustain the war, and that economic collapse happened because Allied bombers could reach their targets and return home. Which happened because the P-51 Mustang escorted them. Which happened because the Mustang had the range and altitude performance. Which happened because of the two-stage Merlin. Which happened because of Stanley Hooker's aerodynamic improvements and Mnemonic 80's ability to survive the conditions inside that supercharger. One alloy, one mathematician engineer, one airframe designer, 3 independent breakthroughs that came together to solve a problem that was killing thousands and threatening to make strategic bombing unfeasible. That's how the P-51 Mustang redefined air superiority, not through courage or tactics alone, but through the unglamorous work of metallurgists and engineers who understood that wars are won by solving technical problems faster and better than the enemy. The forbidden alloy wasn't forbidden. It was just forgotten. But it changed the world.